Harrison, Mark, welcome to the show.
Hey, Jamie, good to hear from you today.
Yeah, thanks for the invitation.
Will we ever see batteries that are 100% made in North America? With tariffs and ever-increasing geopolitical issues comes the increasing pressure to build a robust domestic supply chain to do so. Battery materials are naturally a huge element to achieving this, which is why I was very proud to welcome NOVONIX to take charge with their Anode and Cathode directors joining me to shine a light on how we create a domestic material supply chain in North America. We hope you enjoy. We're recording this on a Friday, which is rare. So happy Friday to everybody listening, no matter what day you're listening on. Before we get into the myths and facts section one, let's do a quick intro to both of you guys and NOVONIX at a very high level. So Harrison, let's start with you.
Yeah, so I'm Harrison Kreafle. I'm Director of Anode Technology here at our Anode Materials division based in Chattanooga, Tennessee. Been with the company for over 5 years now and really focus on the product and process development we do to make our synthetic graphite materials for our customer, as well as I oversee the quality control side of our business as well, making sure that material is the right one for them. And then our business is really focused on just the anode materials side, so making synthetic graphite, just selling that one side into batteries as part of the overall NOVONIX sphere.
And I'm Mark McArthur. I'm the Director of Cathode Technology, and I'm located in Halifax, Nova Scotia. And up here, we focus on cathode materials. So I've been with the company for a little over 7 years now, and I lead up our all-dry, zero-waste cathode processing technology. And just as a quick intro at a very high level to NOVONIX, we're a battery materials and technology company, and we truly provide revolutionary solutions to the battery industry at a global scale to enable the adoption of clean energy.
Thank you, guys. It's been clear for many years that it's a real challenge to create a domestic ecosystem when it comes to battery materials, and now more than ever with the tariffs and geopolitics, never been in a good place. Now more than ever, we need to make sure that it's commercial. We can get this at a good price. So I think today's episode, with you both being on from an anode and a cathode perspective, will provide a nice balance. So section one, we're going to clear up some myths and facts. So the first one is that North America doesn't have a robust enough domestic materials supply chain to commercialize 100% North American made batteries. Harrison, maybe let's hear from you from the anode side.
Yeah, I mean, I would say today it is an ecosystem. There are a lot of components that go into a battery, of which anode material is just one, and the cathode the other, one of the two main criticals. But then outside of that, there's everything you need to actually build the cell, the equipment it takes to make those. So I do think we're making strides in North America, building these cells here today, but there's definitely still is a need with the raw materials, bringing them in. Yeah, and it just goes into more we'll talk about today, but the refining and the processing of those materials to get them to market. There isn't that supply chain today, so we really have to build it, in order for the cells to be made. But the cell manufacturing, I think, is pretty robust here in North America today.
And I would definitely layer on from the cathode perspective that North America is actually very lucky in the fact that we do have significant quantities of these critical minerals. In particular, in Canada, we have a very robust upstream supply chain. However, the requirements on actually extracting those minerals and then converting them into value-add product is indeed lacking, as Harrison was alluding to. So can North America build its own cohesive, singular, vertically integrated supply chain to make these lithium-ion battery devices? The answer is absolutely yes. The ability is there. There are just some parts of that supply chain that need a little bit of propping up, in particular the midstream. And this is where my team really fits in, is in combining those critical minerals, those critical battery materials on the upstream side to really develop that midstream using our processing.
So I guess the key there is, does North America have enough materials domestically? And the answer is yes, on the whole.
Yes. Yeah.
Yeah, but deployed today, I would say there's still work to do for sure to meet the ultimate demand.
The next two cover cost and affordability and performance. So the first one, the second question, North America's battery materials will never be cost competitive to China. What about from an anode perspective, first of all?
Yeah, I think, competing with China, at the end of the day, we're 20 years behind. So there's a lot of catching up to do. And then also, along with that, building and maturing the supply chain. So yeah, today are we at a disadvantage? Absolutely. But that's just, economies of scale haven't hit. Overall supply chain maturation has not hit. So those are all things that have to happen. And I think as they do, and as North America kind of comes online with these items, then we will be cost competitive. And part of what we have to do too, especially with the anode side, is in order to compete side by side, you cannot use the same technology. So I know a lot of what we'll talk about today is how, at NOVONIX, we chose new processes, new technologies in order to make the materials differently so that we could compete on both a cost and a quality basis. But utilizing the current methods utilized today, I don't think we would be able to compete side by side with the time advantage that already exists in the Asian supply chain.
Yeah, and from the cathode side, that Harrison hit all of the points. It's a very similar situation for cathode, whether you're talking about already popular NMC style materials or LFP, building and being competitive to what's going on in Asia is a challenge for North America right now. And this is where new inventive ideas from the processing side of things, from that value add supply chain was really required. And companies like NOVONIX is doing a fantastic job to really turn the supply chain on its head and really make materials the way that we need to differentiate ourselves from Asian suppliers, to ensure that we can produce materials which are competitive while also trying to decrease the cost of production as much as we can for domestic environments.
Yeah, and some of the advantage we do have, Jamie, just to layer on that, is actually the critical materials that Mark mentioned, or in my case, the petroleum coke precursor we use. Those actually do exist in North America today. They're produced and they're typically sold into Asia as feedstock. So we do have a cost advantage to be able to get those locally supplied here without paying the transportation cost kind of back and forth to refine them.
I was going to put you guys in the spot and say, when do we think it will be more cost competitive? I guess with the tariffs coming in, it kind of gives the North America more an advantage. Maybe it's a short-term thing, who knows? But without the tariffs, when do you think North America will be more cost competitive in that aspect?
I think it really depends on the maturity. So as everything builds around us, NOVONIX can't be the only supplier for these materials. We need the ecosystem to grow around us. We need our suppliers to grow, and we need our customers to grow as well. And I think all of that's going to take, it's going to reach a critical mass of scaling that will then enable those costs to kind of be comparative. So, I mean, I would say, definitely within the 2030s, but it really is just a matter of how quickly, I believe how quickly the rest of the market can scale with us.
5 years and 7 months, something like this. Maybe 8 months.
I think your guess is as good as ours there. Yeah, for sure.
Exactly. Much to be done. And then the final question or myth to clear up, and let's maybe start with Mark on the cathode side. So anode and cathode materials from China are of a better standard than those currently produced in North America.
So I'm going to ask a qualifying question. What do you mean by better standard in terms of performance, cost, lifetime? What do you mean by better standard or higher standard?
Yeah, it's quite broad, isn't it? I mean, there's many things. Yes, cycle life, density, all these sorts of things. But in general, the China produce higher quality materials than North America at the moment.
So I think that's in terms of performance, the materials are on par. Anything that is being made elsewhere in the world can be really localized in other locations. It really comes down to how are you producing those materials. On the cathode side, there's very well-established processes to make either an NMC style, like a nickel-based cathode product, or an iron-based product. And the way you make those cathode powders really needs to be different based off of the jurisdiction in which you're residing. But ultimately, when you're talking about cycle life, stability, that kind of stuff, capacity, the materials can be really put to the same kind of standard.
And Harrison, from your side?
Yeah, I would say for our customers, they're not willing to take substandard materials. So what we make for them today has to match like for like or perform better than what they're currently buying out of Asia. So really, there isn't an option to have substandard materials. We have to make them with new methods to meet the performance and then also be cost competitive. So it's really kind of the burden is on us to meet the high quality that definitely is coming out of China today.
Yeah, Mark, I think you cleared up at the beginning there. That's a myth, right? In terms of the actual quality of the materials, why is it all coming from China? Maybe it's driven by cost. So yeah, I think it's encouraging, right? To think that actually we could make this happen. We could make high quality batteries, depending on what your application is, all made in North America. So yeah, thank you guys. That concludes that section. The next one is the guest spotlight. So talking about you guys and NOVONIX and getting deeper into that. So the first question is, it's clear that North America, we kind of discussed this in the myth and fact section, is way behind when it comes to competing on a cost basis with China. And now with the tariffs, the geopolitical issues, and for sustainability purposes, it's clear that we need to produce our own battery materials quickly. So how do you guys see this happening? How do we get this online?
Yeah, I definitely think, like I mentioned, we have to build the ecosystem around us. So we need it all the way from raw materials and equipment to, the maturing of our battery, producers as well within the States. I think that can all happen relatively quickly. And definitely the tariff story, it does enable us to be more economically competitive quicker. But at the end of the day, we do have to produce like for like. So we have to scale our operations. We have to, as we've been doing, and we'll talk more about today, is really changing how we refine the materials, how we produce these out to lower the cost of that manufacturing. And then ultimately, when we're like for like, then it's a no-brainer for our battery partners to accept our materials into the space. But it just takes scale, and it takes a little bit of time to build that scale around you up and down.
Yeah, and as North America has really truly identified that this is a direction that we need to be in, really you need to force the topic, and you do that through government incentives or investment. I mentioned earlier that North America has a lot of the critical mineral supply chain required to build out these value add battery materials to go into the lithium-ion battery ecosystem. However, the midstream is presently lacking. At least in Canada, there's a lot of funding, there's a lot of push to really extract the minerals out of the earth. There's also a large push to generate the lithium-ion batteries themselves that would then power your electric vehicles, your energy storage systems, etc. However, what's lacking is really that midstream, and that's a very critical part of the entire ecosystem to really go from mine to battery, right? So that's really how you accelerate the whole supply chain, is really through investment and really forcing the topic.
It's it's interesting. The last episode we had was Eric Rosenblum from Foothill Ventures, and he was speaking very optimistically about the market, even regardless of the headwinds right now and all the instability. He sees a very bright future, and that some of the biggest organizations in the world will be from the battery space in the United States, that will be commercialized, or North America. So yeah, as you say, forcing the topic is not going anywhere, regardless of what's happening in politics. Hopefully this is just a matter of time, which sounds like it is going to be. Nice. And something I've been thinking about as well is to produce North American made batteries that are commercially competitive. What do you guys think is more important? Do you think it's more around achieving a domestic supply chain, or optimizing the performance, so the material performance?
I think at the end of the day, these batteries are going into high tech applications, whether it's EVs, energy storage, ultimately planes, drones, everything we need, military. So I don't think performance is something that can be compromised on. And today, I feel that's just not possible to compromise. So it's ultimately going to be on us, on these midstream refiners, to make the quality materials that they need in order for the battery makers to make the batteries that they need for their customers. So I think the supply chain is very important, but ultimately they say, yes, this is very important for us to buy your material, but also that material must be the same as what we're getting today to meet our performance.
I may have a bit of a spicy take to this question. So I totally agree with Harrison that the battery material performance is of fundamental importance. It's definitely a requirement. Nobody is going to want a material which is sub-R. After having said that, all battery materials, to Harrison's point, need to have a very similar, I would say, set of metrics by which they are held to that high standard. And the materials that are available on the market today are all very close to whatever that high standard is. When you look at the lithium-ion battery industry as a whole and the materials that go into those battery cells, they're already very high quality. Achieving a 0.5% improvement to capacity retention is a big deal. So any improvement that comes to the materials that go into the batteries are always going to be very small incremental step changes. So the performance of the materials is really dictated and set by the suppliers and the end application. So that really means, to me at least, that the domestic supply chain is of critical importance, because you already have the performance metrics and the requirements for the end user locked in. You can't sacrifice those. But what you really need to do then is to develop the supply chain to produce those materials that do have those metrics, those capabilities that the end user is looking for.
Nice. Yeah, I guess both are important to accelerate commercialization, but what's going to help it accelerate quicker, I think, the supply chain versus performance. Very good. Well, let's get deeper into NOVONIX and what you guys are doing to contribute to this, right? Because there's many organizations like yourselves that are key to ensuring that we deliver a domestic supply chain. So, maybe a high level answer first, and then let's get deeper into the anode side of things.
Yeah, so for us, our key differentiation, we make synthetic graphite. So it's not a mined material. We're taking kind of a petroleum feedstock, and we are converting it into graphite structure. And part of doing that requires very, very high temperatures, close to the surface of the sun. So what we've spent the last years doing in NOVONIX is actually developing the technology to make that heating happen. That's in a very, very different way to what's utilized today out of Asia, which is over 100-year-old process. So we have spent all of our time really. We realized, okay, we know that the way that's traditionally used today is pretty tried and true. It's well understood. But in order to implement that in North America, it just wasn't going to happen. It wasn't going to be able to be cost competitive. There's too much that goes into it that needs kind of the secure supply chain that's built around it today in Asia. But if we were to do it here, we just couldn't. So, that set us on our path to looking for new technology and really going outside the box. So today we're looking at basically a batch process where it's a very, very large batch, almost like an Olympic-sized swimming pool. You fill it with material, you pass electricity through it for weeks, you let it cool for another couple of weeks, and then you harvest it out. You're basically mining it out of that furnace, and that ends up being your end synthetic graphite product. For us, it's completely opposite. It's a closed system, so all of our emissions are captured. It's a continuous system. So as our raw material flows in, our graphite flows out the bottom, and that's continuously happening. So you don't have energy loss with heating and cooling. You don't have any chemicals used in purification. You have much lower scrubbing requirements and also much lower permitting requirements in order to make the same graphite material at the same temperatures, just by swapping really that thermal technology. And I would say that's critical to our differentiation here on the anode side, is how we cook it. And then, outside of that, using a non-batch process for the high temperature, we have also designed continuous processes around the rest of the material. So that just really increases our efficiency. It decreases the number of equipment we use to help lower the cost ultimately, and really enables us to kind of look at that competition by fundamentally looking at the process as a whole, taking it from batch to continuous, and then making it as efficient as possible within that.
And same question to you as well, Mark, on the cathode side.
So while Harrison focuses a lot on actually building out material and producing graphite powder for the industry using our proprietary technology, I take a different route to really commercializing what we're working on up here on the cathode side. We are going hard into the technology to produce nickel-based cathode active material using a process that we call all dry, zero waste. While I mirror Harrison's thinking of we need to be different in North America to really take advantage of a lot of the good environmental aspect of what we are trying to achieve here. The environmental footprint cannot be sacrificed, especially in North America, where we are very sensitive to product and process waste streams. So we have developed a method to generate cathode active material in a completely dry state. Before I get ahead of myself, it's important to take a quick look at what is presently done to generate these NMC-style materials elsewhere in other jurisdictions. Typically, what is done is metal sulfate salts are combined in a process called co-precipitation to generate a precursor active cathode material, or PCAM. That PCAM is then mixed with some lithium to then eventually have a cathode active material, which is nice and free-flowing and could be built into a battery cell pretty handily. Our process really cuts out that precursor process entirely. Rather than making a PCAM, which requires significant amounts of water, and each process through that loop actually generates additional waste, whether that's in forms of wastewater, other heavy metals, or another particularly nasty but benign product called sodium sulfate. We sidestep that reaction entirely, and we directly convert our raw materials. In our case, we like nickel metal, cobalt metal, manganese metal, their oxides, their carbonates, etc., to really cleanly produce a cathode active material by cutting out the PCAM step. And this is a process that we have patented, and we have been really demonstrating that the technology works quite well in our pilot demonstration facility that we established here in Canada back in the middle of 2023. Since then, we've been using our demonstration facility to really showcase and highlight that this technology works for a myriad of nickel-based cathode chemistries, from a mid-nickel NMC all the way to a high and ultra-high nickel NMC. And we've been sampling materials to a variety of tier one users of the material with some pretty favorable feedback. So our goal is to minimize our risk as much as possible, to rather than being material suppliers ourselves on the cathode side, but to take that technology and really license or go through the royalty route.
We work with a couple of clients focusing on dry electrode in the US. It was obviously a kind of popular term being thrown around. Another popular phrase is dry cathode, which I guess is a little bit different. So yeah, Mark, what does it mean?
I get this question quite a bit, and right up front, I need to be extraordinarily clear. So there are two dry processes going on here. There is a dry electrode process, and in my case, the all dry zero waste process. So the dry electrode process, essentially any cathode active material, any anode active material for that in that case, can be combined in a more, I would say, conventional process to produce an electrode itself. So this is essentially any active material can be combined in what I would almost refer to as a cookie dough. And that cookie dough is the electrode material. That would be then laminated onto a current collector, and then it would be constructed into a battery cell. So it's all around the electrode level, not the material level. All dry zero waste allows you to produce a cathode active material in a completely dry state. So the powder itself is produced in a dry process. So the next question, which is usually the follow to that, is can you then use a dry cathode powder in a dry cathode electrode process? And the answer is yes. But we focus on how to make that powder itself in a completely dry state.
I'm in a pre-holiday cut at the moment, and so how dare you for mentioning cookie dough? That just made me super hungry. But that's cleared up really nicely. Thank you very much. And just had a thought. To produce dry cathode in North America, would you say there's more transferable skills to scale that process in terms of the existing talent? Because from what I understand, there's more comparable industries like paper and rubber where it's a dry process versus wet process. There's less manufacturing happening like that in the US. So to actually scale dry cathode manufacturing in the US, is there more of a talent pool?
I would say yes and no. So a lot of the skills in manufacturing are going to be transferable regardless, whether you're going through a wet process or a dry process. I would say, as it pertains to the NOVONIX all dry zero waste process, a lot of the dry processing isn't necessarily the transference of skills, but the environmental savings and potential cost savings using the process itself. With an all dry zero waste process, your waste streams are either nil or extraordinarily low. And because of that, you can operate in corridors which are quite sensitive to waste streams. And that also unlocks doors to potentially savings on actually proper disposal of those waste streams. So going all dry makes a whole lot of sense in a North American jurisdiction where waste streams are extraordinarily important to make sure that they're all accounted for appropriately.
So I've been doing some research beforehand, and if I'm not mistaken, your process focused on crystal NMC cathode powders. How does that differentiate to polycrystal NMC?
Right. Okay. So when you're dealing with NMC style materials, these are the dominant nickel class cathode powders that you would find in an electric vehicle or in energy storage. This class of material can be differentiated between either being single crystal or polycrystal. There was a paper recently put out by Jeff Don's group out of Dalhousie University that really demonstrated one of the biggest advantages of a single crystal cathode powder, and that is the cycle life ability of a single crystal cathode far extends that or exceeds that of a polycrystal. Really, when you get down to the fundamentals and you look at what these materials are, single crystal powders are, as the name entails, a single crystal. If you were to get a hyper strong microscope and look in at what the material morphology actually is, a single crystal is a big rock. It's a single big rock. Each grain looks like a boulder. Polycrystal, on the other hand, is made out of it's like a plurality of single crystals. So you have teeny tiny primary particles which combine together to form one polycrystal powder full of secondary particles. And that's really the differentiator there. So why do you want one over the other? As I alluded to, single crystal is great for cycle life. You want a car to go 1 million miles, 2 million miles, single crystal is what you want. The disadvantage, which is only slightly disadvantageous, is polycrystal powders have slightly better charge rates. So fast charge, maybe a little better. That's the easiest way to differentiate between why you would want a single crystal, why you would want a polycrystal, and what each of those really mean.
I mean, the whole fast charge thing is, there's an argument, isn't there, to how much you really need it. But human nature is we always need things faster. No, thank you, Mark. And before we move on to the next section, which is challenges, it seems like kind of all dry, zero waste technology is a no-brainer from a sustainability perspective, but how does it work from a cost perspective? Are there any advantages there?
Yeah, so I mentioned in an earlier answer, what we do with all dry zero waste processing, we go directly from our raw materials into a finished cathode active material. In the conventional sense, you start with your raw material, you go through that precursor or PCAM stage, and then convert into a cathode active material that could be then deployed into a battery cell, for example. That PCAM process is actually quite intense in terms of capital assets and operating costs. So when you look at it from a million miles high, you say, all right, well, immediately you drop out an entire plant. You no longer need to generate this precursor material to then convert into an active material. So right away, there's huge cost savings just by having a more simplified flow sheet. And if you want to put some numbers against this, we ran a cost comparison study of the NOVONIX all dry zero waste process against the conventional process using our engineering partners. And really the cost savings potential was roughly 30% on OPEX, 30% on CapEx and 50% savings on OPEX, which is really huge when you're trying to set up these new processes to make, as going back to an earlier point, competitive, comparable performing materials for really these North American corridors.
Let's go back to you, Harrison. So far, what have been your biggest challenges to scaling and commercializing, and what can our listeners learn from your lessons?
I think what we're doing most is we're competing against a mature industry. So the products I'm designing, developing today, or that I'm being requested of from our battery partners, is materials that are already mature and developed. So I have to compete, design in a new way materials that are going to be like for like with what they're purchasing today. So that's challenging. And then there's also the aspect of understanding, one, what the customer wants, but then also understanding how the materials that we're producing perform. So luckily, as part of NOVONIX, we have our battery technology solutions group as well. So I'm actually able to produce materials, send it to them, build full cells against comparable materials today out of Asia. We can get industry references, build those cells like for like, and really get that information and get that feedback, and then iterate. The first material I make is not going to be it. It's going to require a little bit of tweaking on our side. So that takes time. And then I think ultimately, then that's time with the customer too. Okay, now we have something that we think is good. We send it to them. We need their validation. We need their buy-in. We need their checkoff. So there's just a lot of time with that. And then, building that too. Okay, we define a process. We define our raw materials, getting them at scale, getting that scaled up. Maybe it's the equipment. We need that to get to a higher size. Working with those vendors, to define that. There's really a lot that goes into it because we're building the whole supply chain. It doesn't exist here today. I can't go buy off the shelf equipment like is available in Asia because they have so much more experience and such a longer time in market. So yeah, it's just really a lot of product dev. And I would say when we started out, we thought, okay, we can make a graphite, we can sell this graphite. But what we really learned working with the battery makers is they have their secret sauce. They have what makes their batteries tick, especially going into their specific end use application. And we really have to meet that. And that took as the company, that took a little bit of time to figure out too. And that would be kind of my warning to anyone going new into the space: figure out what your customer wants and work towards that. First, and then understand that it's going to take time to do that iteration and make these materials what they want.
Question to both of you: if you were to paint a perfect picture of NOVONIX in 5 years' time, what would we all see? And Harrison, let's start with you.
What I always think is I want to be driving down the road and see a vehicle and say, my material is making that happen. Like one component, sure, but something that I designed, something that's being made in our factories is in this vehicle, or outside of a solar field and energy storage, or flying in a drone. I want to see a product that has our materials in it and really have that. I mean, being business to business, we'll never have kind of the brand name recognition. I don't think we'll ever be a Duracell, but having the pride in ourselves of saying like, okay, well, this Stellantis automobile has NOVONIX materials in it and is making it go. That is where I think we will be, and where I want to see us in 5 years.
I think you stole my answer, Harrison. But no, to layer on that again, I can add on. I know when I started here back in 2018, when I started at NOVONIX, I have been familiar with NOVONIX since its inception in 2013, and I primarily recognized it as a Canadian company first, that then transitioned to the behemoth which it is today. And I again, it's going to be kind of the wishy, sentimental response, but I feel very proud to be able to say that I worked at a company that started in Canada that began this great journey to eventually be getting materials sold and put into different end applications, right? But at least going from the Canadian side, having a company that has strong roots here is a really good thing to me, and I want to keep pushing that narrative as we move forward over the next 5+ years.
Well, hopefully we can see that picture in 5 years. If we said, well, for 5 years, I think it was 5 years, 7 months, wasn't it? We said for commercialization. Great. So, a couple of questions from the community. The first one is, what are the biggest technical or logistical bottlenecks right now in building a fully domestic battery material supply chain in North America?
I think for us, being a first mover is not necessarily a first advantage because we are building the supply chain with us. We're figuring out how to do it actively as we go. So that is a challenge, and then really getting the equipment, installed, built, and ready to go, making the materials you want is a challenge, and it's also very capital intensive. We have to build these factories, so you figure out how to do it. You get your product defined, and then you have to build it out, and it just takes time. But luckily with our process being very clean, permitting, that sort of thing is not generally an issue for us. So that helps us with our timeline. But still, really, really getting the equipment on the ground to make those materials and getting into the customer's hands is what takes the time.
And I would say from the cathode perspective, the battery industry as a whole is not new, but it's not old either. And these processes and the technologies which are really backing the materials, backing the cells, the companies that are involved are very risk adverse. They do not want to take risks when it comes to new process technologies. So one of the largest, I would say, hurdles in North America is trying to adopt a technology that works in other jurisdictions like Asia, and trying to push that into North America is very challenging. We in North America need to think a little differently because of some of the comments I made earlier around waste and costs. So really that I find is one of the biggest hurdles, is just technology adoption, having that willingness to make the product we all know we want to end up making, but making it in a different way that's more either socially responsible or environmentally responsible.
The next one's tongue-in-cheek, a bit silly, to be honest. I think the person asking knew what they were doing, but they asked, did you have a good NP ratio? Negative and positive ratio.
So I'll jump in there. So what is an N to P ratio, first and foremost? So when you're constructing a lithium-ion battery cell, for safety reasons, you want to make sure that you match your electrodes. And what I mean by that is you want your negative electrode, your graphite in this case by Harrison, has to have a little higher capacity than your cathode material. And there's a lot of technical reasons that I'm not going to dive into as to why you would want to do that. But it's very important that every battery cell that's in your laptop, cell phone, etc., has a little higher negative capacity than a positive capacity. We at NOVONIX are not cell manufacturers, at least at widespread scale. However, our team here up in Canada, we have the ability to produce battery cells at I would say, R&D level. And we always try to ensure that our N to P ratio is, I would say, 5 to 10% excess anode to cathode material. So to answer the question, what is it? It's greater than 5%.
Yeah, so I think at the end, Mark and I always joke, they need 5% more of me than they do of Mark.
In all seriousness, is it beneficial to be working together? Because I know a lot of companies will focus on cathode materials or anode materials or even electrolyte, but doing it together, is that beneficial?
I would say so. I think there's a lot of transferable skills. There's a lot of transferable knowledge between my teams, development teams, and Mark's, as well as being in the NOVONIX ecosystem, having our battery researchers as well in the services division. We really are able to pull from each other, all in all, and really see the full side. Like I could see how my materials impact Mark's, vice versa, and then we could see how both of ours compare against what's out there today. So it really is a nice ecosystem we've built with each other, and a lot of transferable skills. Some of the equipment is really quite similar between the two material manufacturings, and I think we had best practices and learnings from installing those and operating them. especially with where we're at, we kind of have our process developed. It's really more of just scaling now. So I'm a little bit ahead of Mark on that side. So, over the last few years, been able to work with this team, my team collaborating with his on those learnings, hey, we know what not to do now. Here's some advice for you guys, and take it or leave it.
So like a positive, negative cop, like good cop, bad cop. Thank you, guys. One final question, which is from a former guest. You obviously don't know the question. I can't tell you who asked the question as well. It's always selected at random from a bunch of previous guests. But this is quite a nice one, actually. And again, I'll take an answer from both of you. The question is, what application area would you truly like to see take off in North America? Not necessarily the application area that you think will take off.
I'll go ahead. I think for me, it is energy storage. What I really want to see is these deployed megawatt scale, effectively containers full of batteries everywhere. I think it helps with our grid resilience. I think it's going to enable our move to renewable energy easier. But ultimately, it's gonna balance everything out. If you're producing more energy during the day or during night, depending on where you're at and what kind of energy generation you're using, this can really level the playing field and put the power where you need it, when you need it. We've been hearing a lot about it in the industry now for data centers. That's the kind of the primary contributor of this need. But that, to me, that's just one use case. I think having it at every distribution site in every neighborhood is really going to be huge for just the resilience of us. With storms, with outages, national security. It really just helps hedge your bets against that. So I'm really excited about the energy storage space. Of course, EVs are cool. Drones are cool, electric planes are cool, but energy storage is really the meat and potatoes of the energy transition and our national security.
I think Harrison stole my answer again. I can answer the counter to that question, which is what sector I do not want to see, but I'm not going to say that answer. No, honestly, like I mirror what Harrison says about energy storage. If we're going to be really fun and out there, I would definitely like to see more space exploration. I know North America is doing quite a good job there. After having said that, there's a lot of advantages that are up out there. There's a lot of critical minerals out in space that we could potentially take advantage of. For example, space mining. You want to talk about critical minerals which are on our planet? Well, there's a lot more that are out in the wild space of really the galaxy, right? So space exploration and mining is something that I feel there is a huge gap to fill, especially when we're dealing with a sustainable planet. So in order to really continue life and make humans happy, I think we need to really see what else is out there and take true advantage of really thinking well beyond the box of what else is out there to really help sustain human life.
Definitely. I think it depends if you want to give a sensible or an exciting answer. Yeah, could eVTOL, for example, that's space as well. Super cool. And it's quite fitting, actually. It's well timed because this Monday we had the blackout here in Spain and Portugal, where literally we were off grid, and as well we didn't know what was happening, like no phone signal, no nothing, and we didn't know when we were going to come back online. So again, can batteries play a role there if this is going to happen in the future? They called it an environmental phenomena. They still don't know what's really happened, but yeah, can batteries play a role in protecting us from that in the future? Because that was bad. But gentlemen, thank you very much. Really appreciate your time today, and good luck for the next 5 years and 7 months.
Appreciate it. Thanks very much for the opportunity.
Thanks for having us, Jamie. Great talking to you.